What would it take to turn a curious observation into a clear, testable prediction? Imagine this. You're designing your first research project. Maybe you've noticed that students who listen to music while studying seem more relaxed, or you've read about how caffeine might influence memory. But before you dive into data collection or statistical tests, you need something solid, something specific and scientific to guide your work. You need a research hypothesis. But what exactly is it, and how do you write one that holds up under scrutiny? Crafting a strong research hypothesis isn't just about guessing an outcome. It's about defining a relationship between variables, identifying what you'll measure, and stating clearly what you expect to find. A well-formed hypothesis can steer your experiment like a compass. It tells you what data to gather, what patterns to look for, and how to interpret your results. In other words, it's the foundation of the scientific method. First, what is a research hypothesis? At its core, a hypothesis is a testable statement about how two or more variables are related. It's often framed around a cause and effect, like how caffeine cause might influence memory effect. But not all hypotheses are created equal. Some are precise and predictive, others are open-ended, inviting exploration. You begin by identifying two things: your independent variable, the one you manipulate, and your dependent variable, the one you measure. Then you formulate a statement that predicts how changes in the first will affect the second. For example, if students consume caffeine before a memory test, then their recall scores will improve compared to students who do not. Next, types of hypotheses. Not all hypotheses point in the same direction. Some are bold and specific, others hedge their bets. A null hypothesis, H0, states there is no effect or no relationship between variables. Caffeine has no effect on memory performance. This is what you try to disprove with data. An alternative hypothesis, H1 or HA, is what you're actually testing. It proposes that there is a difference. Caffeine improves memory recall in students. Some hypotheses are directional, meaning they predict which way the effect will go. Sleep-deprived students will perform worse on math tests than well-rested students. Others are non-directional, saying only that a difference exists without guessing which group performs better. There will be a difference in math test scores between sleep-deprived and well-rested students. Also, simple hypotheses involving one independent and one dependent variable, and complex hypotheses, which might involve multiple variables or predicted interaction. Students who drink caffeinated beverages and listen to music while studying will show better performance on verbal tasks, but worse on math tasks. Then, making your hypothesis testable. It's not enough to say, "I think this will happen." A hypothesis must be operationalized, translated into variables you can measure. If your hypothesis involves stress, what exactly are you measuring? Heart rate? Self-reported anxiety? Cortisol levels? A vague hypothesis might say, people feel worse when they use social media too much. A strong one would say, participants who spend more than 3 hours per day on social media will score higher on a standardized anxiety scale than those who spend less than 1 hour per day. Good hypotheses are specific, measurable, and falsifiable, meaning you could design an experiment to prove them wrong. And finally, why it matters. A clear hypothesis does more than just predict results. It shapes your experimental design, your data analysis, and your interpretation. It keeps your research focused and purposeful. Without a hypothesis, science becomes aimless. With one, you turn curiosity into discovery. So, can you write a good research hypothesis? Yes. But it takes clarity, precision, and a little courage to commit to a prediction. Because, in the end, a hypothesis is a statement of belief, but one that dares the universe to prove it wrong. And that's the first step towards scientific truth. The research hypothesis paradox refers to the intriguing dual nature of a scientific hypothesis. It must be bold enough to propose a new relationship or effect in the world, yet precise and narrow enough to be tested with available data. This balance between innovation and measurability challenges both beginner and expert researchers alike. Crafting a good hypothesis requires transforming a broad curiosity into a focused statement that makes clear predictions, testable, falsifiable, and framed within a methodological plan. A vague curiosity like, do people learn better with visuals, becomes a testable hypothesis. Students exposed to video-based tutorials will score higher on comprehension tests than those using text-only materials. It's like turning a dream into a blueprint. Ideas must be translated into structures that can be built, tested, and revised. A research hypothesis is a declarative, predictive statement that proposes a specific relationship between variables. It emerges from the research question and provides the logical anchor for designing experiments, collecting data, and interpreting results. A strong hypothesis identifies independent variables, is based on theoretical rationale or prior findings, and can be supported or refuted through observation or measurement. For instance, a hypothesis such as exposure to blue light for more than 2 hours before sleep reduces melatonin levels in adults serves this purpose well. It's like aiming an arrow. You're not shooting into the dark, but toward a defined target that reflects your question. Hypotheses can be classified based on form, function, and directionality. The null hypothesis H0 suggests no effect or relationship, e.g., there is no difference in reaction time between caffeine and placebo groups, acting as the scientist's control. A line in the sand you challenge with evidence. In contrast, the alternative hypothesis H1 or Ha proposes a predicted effect or difference, e.g., caffeine consumption leads to faster reaction time than placebo, much like a theory taking its first step. It wants to walk, but must be tested for strength. A directional hypothesis specifies the expected relationship, e.g., increased screen time leads to decreased sleep quality, indicating not just if there is a path, but which way the river flows, while a non-directional hypothesis predicts a difference without specifying its direction, e.g., there is a significant difference in academic performance between urban and rural students, similar to a compass spinning freely, you know you'll move, but not where. Statistical hypotheses frame claims numerically, e.g., H0, M1 equals M2, vs. M1, M2, like framing your question in mathematical grammar, ready for the courtroom of data. A hypothesis is not plucked from imagination. It is derived through a process of synthesis from background literature, theoretical models, gaps in knowledge, and logical deduction. The process transitions from observation to research question, then literature review, conceptual framework, and finally hypothesis, with each step narrowing the scope and crystallizing curiosity into a testable claim. For example, one might observe that some plants seem to grow faster under colored lights, pose the question, does light color affect plant growth? And develop the hypothesis, plants grown under red LED light will have a higher biomass than those under blue light. It's like chiseling a rough stone into a gemstone. The sparkle comes only with clarity. In complex systems research, a hypothesis helps isolate specific interactions within broader interconnected phenomena. It acts as a probe, targeting one potential causal relationship at a time, allowing researchers to map nonlinear systems, test feedback loops, and build mechanistic understanding, even in intricate fields like neuroscience, ecology, or social dynamics. For instance, in a study of academic burnout, a hypothesis might isolate one factor. Students with less than 6 hours of sleep will report significantly higher burnout scores than those with 8 hours. Much like isolating one switch in a complex control panel to see if flipping it dims the lights. A hypothesis defines the direction of inquiry and the flow of analysis, from assumed cause, independent variable, to predicted effect, dependent variable. It sets the stage for experimental energy allocation, determining what to manipulate, what to measure, and how to interpret deviations from expectation. For example, if the hypothesis states that sugar intake affects memory performance, experimental energy is focused on dietary control, memory testing, and ruling out confounders. It's like setting a river's course. You guide the flow of inquiry through a channel cut into the unknown. In information theoretic terms, a hypothesis compresses expectation into a single predictive statement, a low entropy claim about what should be observed. If the data violate the hypothesis, the informational gain increases. Thus, good hypotheses are precise, falsifiable, and rich in information yield. For example, stating, reading aloud improves vocabulary retention in children compared to silent reading, compresses a set of learning mechanisms into one efficient statement. It's like sending a concise message through a noisy channel. The clearer the signal, the more surprising the contradiction. Strong hypotheses are essential for grant proposals, peer-reviewed papers, dissertations, and experimental design because they signal intellectual clarity, methodological discipline, and scientific creativity. Poorly framed hypotheses waste time, obscure results, and hinder reproducibility, while a well-articulated hypothesis frames your study and invites others into your logic. For instance, funding agencies prioritize proposals with hypotheses that clearly link theoretical gaps to testable outcomes, ensuring that knowledge is built incrementally. It's like laying the foundation for a bridge, not flashy, but if crooked, everything collapses. Common pitfalls in hypothesis generation include vagueness, confirmation bias, overcomplexity, and underpowered testing. Good research training emphasizes falsifiability, simplicity, and the willingness to revise hypotheses post-analysis. For example, a hypothesis predicting all variables will correlate is unfalsifiable and uninformative, so selecting one plausible direction to explore is critical. It's like casting a fishing net across the whole ocean. You catch nothing of value if you don't focus. The future of hypothesis writing includes AI-assisted generation, dynamic hypothesis trees, and integration with Bayesian reasoning, where researchers update beliefs in real time as evidence accumulates. In education, hypothesis generation will become a core skill taught early, alongside data literacy and critical thinking, training young researchers to think not only like scientists, but like systems designers. Tools like ChatGPT or Elicit can now assist students in formulating testable hypotheses based on literature input, accelerating the research ideation process. It's like having a scientific co-pilot, helping navigate from the fog of curiosity to the runway of clarity.